Hello friends, this is part 4 of question paper solution, paper C-13 2022 of 6th semester Dibrugarh University, Electromagnetic Theory, right? So we have already solved up to question number 4. Today we're going to solve question number 5. Before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. And if you want to follow me on Insta, this is my Insta ID OJHALAKHYAZIT 123. This is my Insta ID. Follow me on Insta. So now let's start. So here is the question number 5. What is waveguide? Describe the propagation of electromagnetic wave along hollow waveguide of uniform cross section. Explain how cutoff mode arises. Okay, so here you see this is the definition of waveguide I have written. Then I have considered the propagation of electromagnetic wave in a inside a hollow conductor of uniform cross section. The walls are perfect conductors, right? I have considered the walls are perfect conductors. Then the wave equation for the electric field will be given by this equation number 1, okay, where del square is Laplace operator. So hope you know this. And solution of this will be given by this is the desired plane wave, right? Solution. And here you see this represents the wave is propagating along z axis, right? Okay, and the amplitude here E0 is the function of x and y, and wave is propagating along z axis, right? So, and kz is the guide wave number. And let me go to the next slide. So like for electric field, we can write similar equations for magnetic field as well, but we are not going to write here all the equations. Okay, so now, so using 2 and 1, if we use equation number 2 and equation number 1, then we can write this equation, right? So what we have done here, let me tell you, you can see that del square here, it means del square by del x square plus del square by del y square plus del square by del z square, right? So here you see I have taken that transverse Laplace operator that consists only these two, okay, so which can be written as Laplace operator, that is del square minus del square by del z square, because it consists all the three, del square del x square plus del square del y del square by del y square plus del square by del z square. Okay, if you subtract this, then you're gonna get this one, right? So hope you have understood this. So that's why here what we have done, okay, instead of this del square, what we have written, that we have written this, you see this part is replaced by this, okay, and this part is replaced by kc square, okay. So hope you have understood this. So how to obtain this equation, how we have obtained this equation, just what we have done here, let me clean this, okay. So we have used equation number 2 in 1, this result, okay. If you replace this by this result, then you will get this equation number 3, right? Now you see here This is equation number 4. Now let me go to next slide. So equation this field E, it consists of two components, Ez and Et. Similarly, B also consists of two components, Bz and Bt. Okay, so these two are the parallel and these two are transverse to the axis of the conductor, that means the z axis. We have taken the axis of the conductor as z axis, right? So where Ez can be written as E naught z e to the power this, then k cap is the unit vector along z axis, and the transverse component consists of E naught t vector e to the power this, then, and this part consists of x component and y component, right? Hope you have understood this. Now this field must satisfy the Maxwell's equation. This is the first equation which can be written this way, like equation number 7, right? So here what we have done, we have instead of this E, what we have written, we have here you see we have used this, and instead of these two we have used these components. Okay, and taking the dot product of E and del, we have got these equations. Similarly, second Maxwell's equations, that is here equation number 8. This is the second Maxwell's equation, and from the third one, del cross E. How to find the del cross E? Cross product del cross E. So here we're gonna write I cap j cap. So if I write only I, that means that is complex number, imaginary number, root over -1. If I write I cap, that is unit vector along x-axis, remember that. Okay, and j cap, and del cross means del x plus del y and del z, right? Then del cross E means you have to write the x component, y component, and z component of E, that is E0x, then e to the power whatever you have got, then again E0y, then again E0z, e to the power ik, whatever you have got here. You can see e to the power this, that should be written. So if we evaluate this, then we will get this result, right? Sorry, this equation, this tree we're gonna have from that cross product, right? Similarly, del cross B will give these three equations. Okay, now we're going to solve these equations. First we're going to solve 10 and 12. If we solve 10 and 12, then what we're going to get, here you see this this IBOY will be replaced by this value IBOY, that will be equal to 1 by omega of this, right? So we're gonna put this value here. Okay, hope you have understood this. Then we're gonna get this equation, right? So let me show you how. So here you see I have taken both the equations 10 and 12. I'm gonna show you how to solve these two, but you don't need to show in the answer sheet. Okay, for better understanding, I am going to solve these equations now. Now you see this equation number 10. Equation number 10 will give IBOY 1 by omega IKG EOX minus del EOZ by del x. That's what we're gonna have. Now let us replace this IBOY by this value. Then this equation number 12 gonna give you 1 by y BOZ minus kg. Instead of IBOY, we are going to have 1 by omega within bracket I kg EOX minus del EOZ by del x is equal to minus I omega c square EOX. That's what we have got. Now if we simplify this, del BOZ by del y minus I kz square by omega eox minus minus plus kg by omega del x of eoz minus I omega c square eox. So let me write eox on the same side. So then we're gonna have minus I kz square by omega eox minus, that's gonna be plus I omega c square eox. On the right hand side we're gonna have minus del boz by del y minus kz by w del x of eoz. That's what we're gonna have. So here you see, from here what we can do, we can take I by omega common. If we take I by omega common, right, I by omega common, then within bracket what we're gonna have, this gonna be I is taken common, omega is square, then eox is also taken common, then we're gonna get this equation, right, after taking common, right? Hope you have understood. And as I have already mentioned, this is equal to kg, right? Sorry, not kg, ksc square is equal to this one. We have already mentioned here, you see. Okay, where I had mentioned this, let me show you this one. Kc square is equal to this. So here you see, so this will be replaced by kc square. Okay, then this equation will be of this form, kc square equal to kc square eox is equal to this. So now, so eox will be equal to minus omega by kc square, right? Sorry, I kc square, and within bracket we have got this after taking minus sign common, this will be plus, right? Now you see, if we multiply this omega with this, and then this omega will be cancelled, right? So we're gonna get kz here, right? Here we're gonna get 1. So if we multiply I on both sides, both numerator and denominator, I that's gonna be minus 1, so it's gonna be plus. That's what you're gonna get, right? So that's how we have got this equation. That's how we have got this equation, right? So hope you have understood this. Similarly, if you solve equation number, sorry, let me check which one should be solved. Okay, equation number 13, and equation number 9, equation number 13 and 9. Solving equation number 9 and 13, we're gonna get this result, equation number 16, right? And from these two, equation number 15 and 16, what we can do, you see, equation number 15 and 16. Now you see, this EOT is equal to EOX I cap EOY j cap, right? As I have already mentioned here, this one, you see, it consists of two components, EOX I cap and EOY j cap, right? So here I have written in this way. Here you see, sorry, I'm taking here EOT, this one, sorry, this one. EOT is this one plus this one, right? So this part is here, okay? So that's why we have used the 15 and 16, equation number 15 and 16, okay? Then we have got this, okay? After simplification we have got this, right? And this 2 can be written. So now you see, once we have put this 2 in place of EOX and EOY, we have rearranged the terms as you know, EOZ and EOZ, then BOZ and BOZ. We have separated, right, into different brackets, B and E. Okay, so then we can use the operator. Okay, then we will get the here you see 4 transverse electromagnetic wave. Transverse electromagnetic wave, that means this kind of wave. Okay, this transverse electromagnetic wave, if the wave is propagating along z-axis, that amplitude cannot be along z-axis, it may be along x and y. Okay, so this amplitude can have x and y component, but amplitude cannot have z component while it is moving along z-axis, right? Hope you have understood this. So if we use this value in equation number 7 and 8, let me go back to the 7 and 8 where we have got 7 and 8, these two equations 7 and 8. So these two parts will be 0, right? So then we will get this one plus this one equal to 0, and this one plus this one equal to 0, because these two terms gone 0, right? Hope you have understood this. So that's why we have written here these two equations. I have given both the equations, equation number 18. Similarly, from equation number 11 and 14, where are the 14 and 11? So this is 14 and this is 11. From these two equations we're gonna have these two equations, right? I have taken these two as 19. So taking partial derivatives of 18 and 19 with respect to x and y respectively, we're gonna get these two results, and which shows that there cannot exist transverse electromagnetic mode within a hollow guide with the perfectly conducting walls, and for transverse electromagnetic mode to exist, it is necessary to have 2 or more connected surfaces. That is the conclusion that we have got. Now the last part of the question was that why this cutoff mode arises, that because of the dimensions and the boundary conditions of the waveguide. Okay, so here you see, so let me show you again. This is the first piece, this is the second, take the screenshot, this is the third piece, this is the fourth piece. Actually this is fourth piece, and this is fifth, and this is sixth, you can see, right? First you have to write this part, then this part, then this remaining part. Okay, right? After that this is 7, okay, this is 8, then this is 9, right? So there is another question, question number 5, or 4 transverse electric waves perfectly propagating in rectangular waveguide with perfectly conducting walls. Find cutoff wavelength and the velocity with which energy is transmitted along the guide. So let me show you how to solve this. So this is the question number 5 or answer. So you have to start writing from here. This is page number 1. Take the screenshot or pause the video, you can note it. The next page is this, then the next page is this one. Okay, this is the 4th page, and from here we're gonna find this is cutoff frequency. Now we're gonna find a cutoff wavelength. Let me show you how to find it. First let me write the cutoff frequency expression again. Let me write this expression on the new slide again. That is nothing but what was that, pi c, okay, omega is equal to, omega c is equal to pi c root over m by a whole square plus n by b whole square whole to the power 1 by 2. I think there was omega mn here, yes. So this was the expression, right? So now cutoff wavelength cutoff wavelength is given by that lambda c is equal to c by fc. Now let us obtain this. Now fc is nothing but here you see omega mn is nothing but 2 pi fc. This is the relation between fc and omega. So if that is the case, then we can write this is equal to this one, right? And from here let us obtain fc. So here pi will be cancelled, then this 2 comes here, so c by 2, that's why fc is equal to, that's what we have got, right? So now let us put this fc here, then we're gonna get the cutoff wavelength, that gonna be equal to lambda c is equal to c by 2 root over m square by s square plus n square by b square. That's what we're gonna have, whole to the power half. So here c gone, so we're gonna get 2 by root over m square by a square plus n square by b square. That's what we have got, right? Okay, so this is the expression for cutoff wavelength, and velocity with which the energy is transmitted, that is given by the group velocity. Okay, therefore the velocity with which the energy is transmitted is Vg is equal to del omega by del d omega by dkg. Okay, right? So hope you have understood this. If you have understood, please do subscribe the channel, hit the thumbs up button, and also share with your friends. So see you in the next video. Bye bye.